So today it's my pleasure to welcome Professor Vitaliy Kurlin and Dr. Daniel Widdowson, who are giving a joint talk today, and their title is Resolving the Data Ambiguity for Periodic Crystals. And Vitaliy, I think you're going first, so if you're able to share your slides.
Thank you, John, for your nice introduction. The talk will consist of two parts. So first, I'll introduce our geometric methods for periodic crystals, and then Daniel Widdowson will give a live demo of his crystal geomap that he developed for visualizing materials databases. If you have any questions during the talk, so please ask. And especially during our break between our talks. So in our research, we study all types of periodic crystals, and the motivational quote for us is from John Maddox's editorial in Nature almost 40 years ago about one of the continuing scandals that it remains in general impossible to predict the structure of a crystal from its chemical composition. So here I have highlighted two words, continuum and structure, because these words will be very important in our presentation today. Okay, well, crystal structure. If you open any crystallographic textbook, you will probably find a definition similar to the following. So we start from a basis in Euclidean space, for example, say a couple of orthonormal vectors in the plane. This basis generates the unit cell, so spans the unit cell, and also generates the periodic lattice consisting of all integer linear combinations of basis vectors. So that's how we get a lattice. But also immediately from this very basic definition, you might notice that you can get exactly the same lattice, so here consisting of all these black dots, starting from a different basis. So instead of this green one, you could take the same vector v1, but also the sum of v1 plus v2, which generate a different unit cell, but exactly the same square lattice as a set of all linear combinations. So more generally, for periodic crystals, in addition to a basis, in addition to a unit cell, we fix a motif of atoms inside, and then simply take the sum of all lattice vectors and all motif points, and that's how we get a general periodic set of points representing a periodic crystal. And this picture shows that the ambiguity of this representation becomes even worse, because even for a fixed unit cell, you could choose very different motifs inside, and from these different motifs with exactly the same unit cell, you could generate the same periodic set of points. Or more exactly, these periodic sets of points will differ only by translation, by a choice of an origin for our basis. So what crystal structures actually should we call equivalent in this case? So the word equivalence is a very basic concept in many sciences, not only in mathematics. So an equivalence is a binary relation between any types of objects, in our case, of course, crystals. And this binary relation is called an equivalence if it satisfies the three basic axioms: reflexivity, symmetry, and transitivity. And here transitivity is especially important because it justifies a classification as a splitting into disjoint classes. So what equivalences can we consider for crystals? So chemists probably like chemical composition. So you could say that two crystals are equivalent if they have the same composition. Yes, this is certainly a well-defined equivalence. However, even school kids know that there are materials such as diamond and graphite, for example, that have the same chemical composition but very different properties, so they should be distinguished in a different way. Crystallographers traditionally classified crystals by different equivalents, by symmetries, or more exactly space group types. And at the end of 19th century, it was a great achievement to list all these space groups in 3 dimensions, so 230 classes if you distinguish mirror images. However, many chemically different crystals still are in the same class, have the same space group. So that's why the question same or different still appears in titles of crystallographic papers. So that's how we come to another equivalence relation, which is very much motivated by simply crystal structures. So when you look at a real crystals, such as this rough crystal of silicon, you might notice that it looks rigid. So what does it mean? It means that if we transform our crystal structure by rigid motion, so if we simply translate or rotate our crystal, so changing its representation in unit cell basis, when the underlying crystal structure remains the same, at least under the same ambient conditions, such as room temperature and pressure. If in addition to rigid motion, translations and rotations, we also include compositions with reflections, we get a slightly weaker equivalence of isometry, which I will be using often in the slides, but we distinguish. So rigid motion is stricter, practically the strongest, but isometry is only slightly weaker. We do not distinguish mirror images. So since crystal structures are determined in rigid form, this motivates a new definition of a crystal structure, not as a representation in terms of a unit cell and fractional currents of atoms in a fixed unit cell. So not as a traditional C file, but as a class of all these infinitely many representations that are equivalent to each other under rigid motion, which is the strongest equivalence in practice, or slightly weaker, if you don't worry about mirror images, slightly weaker under isometry. Any questions at that point? Because this is the main concept that we introduce. So abandoning the traditional unit cell approach and defining it rigorously in terms of a rigid motion, so justified simply by rigid structures of real crystals. Okay, and this slide visualizes challenges that crystallography faced over many years until very recently. So if you see any periodic crystal, here you have an example of a hexagonal lattice, but it applies actually to any periodic set of points. So take your favorite crystal, when it's very tempting to reduce this infinite periodic set to a finite subset. Yeah, it's very tempting, but unfortunately it doesn't work, because you could take a cut-off ball or a box of sufficiently large radius or size, and different boxes or balls of the same size, they contain inside any given periodic set of points different finite subsets. So you could have even different numbers of atoms inside a ball or box of the same size. So that's why it's completely not trivial to reduce a periodic set of points to a finite one. Finite sets can be very ambiguous. That's why we should not forget about a unit cell. However, if we base our analysis on a unit cell, then there is the ambiguity of choice for a basis, but also under rotations and translations. So we could even translate a motif inside a fixed unit cell, changing the traditional representation in a C file. But the main challenge of traditional representations is this discontinuity illustrated in this row. So hexagonal lattice has a small primitive cell, a parallelogram or rhombus shown here. And this more conventional rectangular cell is not primitive. Yeah, it also can be used for representing a hexagonal lattice. But under very small perturbation, if we shift every central atom in all these rectangles, every central point, then this yellow cell becomes primitive. So it is no longer non-primitive, it is primitive under a very small perturbation. Under almost any perturbation, it becomes primitive, twice larger than the original. Or if you apply a slightly different perturbation, we could make even larger, 4 times larger primitive cell. Or we could actually scale up the initial primitive cell by any integer factor. So under very small perturbation, you could start from any crystal, not necessarily hexagonal lattice, not necessarily a cubic crystal, any periodic crystal, like this one, and you could consider it within the space, small enough space of crystals that have the same fixed size of a motif, so the same number of atoms in a fixed cell, but also the same crystal is infinitesimally close to a larger subspace of crystals with twice as many atoms in a primitive cell, or 3 times larger unit cell, or any times larger. So as a result, our space of periodic structures is actually very complicated, because every periodic crystal here is a singularity. So totally singular space, because we have intersections on all the spaces at every point. So these are the challenges, and let me finally illustrate the paradox, because one of the reviewers of our papers asked whether there is a paradox here, and indeed it is a paradox. This Sarita's paradox has been known from ancient times, and usually illustrated by a heap of sand. So you have a big collection of some objects, yes, too many grains of sand, and you start removing these grains one at a time. So if you remove only one grain of a million or very large number, does we have still the same heap or different? If we have still the same heap, then can we continue removing these grains until after many steps, it becomes simply empty? So if you have always the same heap, then how could we get no sand at all at the end? So this paradox applies similarly to periodic sets. If we perturb slightly our atoms, and accidentally a unit cell becomes twice larger, so if we ignore this noise and call the initial set as 1 and its perturbation is 2 equivalent, or sometimes like called pseudosymmetric, for any small threshold epsilon, then by the transitivity axiom of an equivalence, we are forced to say that all periodic sets become equivalent, because we can construct a sufficiently long chain of perturbations similarly to the heap of sand, making it disappear, and similarly making all crystals equivalent. How can we resolve this paradox? The natural resolution would be when we make a change, we should register this change. So we should not ignore noise, we should simply measure this noise. And that's what we are going to do. So the formal problem, so here stated for periodic sets of points representing crystals, but actually the same problem we state here makes sense for many other objects. So in the simpler case for molecules, or you could consider even disordered materials, so any objects you like. So crystals, we would like to construct actually an analog of a genetic code for crystals. We call it briefly geocode, which satisfies the following conditions. So this geocode, ideally a collection of numbers. So you will see numbers and maps for these geocodes later, but for a moment you could imagine it as a simply collection of numbers. So 2 crystals, isometric or rigidly equivalent, a little bit stronger. If isometric, then this geocode should take the same value. So we call it, in this case, invariant. And one simple example of invariant could be, say, physical density. Yes, it's invariant if 2 crystals are rigidly equivalent, then of course they have the same physical density. In the language of computer science, it means that invariant is a descriptor with no false negatives. The second condition is much stronger. It says that this invariant I should be complete. So it completely distinguishes all non-equivalent objects. Or more, in other words, if the invariant takes the same value, then this can only happen for equivalent objects, so for isometric crystals. So a descriptor with no false positives on all possible data. Continuity. So you have seen that under very small perturbation, Traditional representation changes discontinuously. That's why it's important to guarantee that under small perturbation, our invariant changes continuously. So here stated in a strong so-called Lipschitz form, if every atom is shifted a little bit up to epsilon Euclidean distance, then the invariant changes up to a constant, fixed constant lambda times with amount of perturbation epsilon. So these are not all conditions, because mathematicians can easily solve this problem by simply taking an invariant of some infinite size. For example, the collection of all crystallographic information files representing one crystal structure. This would be a trivial but not practical solution. That's why we need not only complete and continuous invariants, but we need to good invariants, like particularly fast to compute. And fast to compute, here we say in polynomial time in the input size, which is the number of points of atoms in a unit cell. And additionally, we would like to have these invariants to be simple enough so that we can go back and reconstruct any periodic set of points from its invariant value I of S. Okay, if there are no questions so far, then let me start introducing the invariants that will be solving this problem step by step. So here you see three examples: the square lattice on the left, hexagonal lattice in the middle, and so-called honeycomb structure or graphene-like structure with this hexagonal pores in the plane on the right-hand side. So what we can do in these simple cases is the following. Say for a lattice particularly, we could fix the origin at any point. So let's start from one point and write down distances to other points in increasing order. So in the square lattice, we have four neighbors at distance 1, for example, for size 1. So write them down with values equal to 1. Then fellow neighbors with diagonal corners are at distance √2. So we continue writing down these distances, and that's how we get this infinite sequence of distances to neighbors. For the square lattice, for the hexagonal lattice, it looks a little bit different. And for this honeycomb structure, since we have several points, so a couple of points in a unit cell, one simple way to avoid the dependence on ordering with points is to simply take the average. And that's how we get the average minimum distance. So it's the average distance to the cave atomic neighbor. So here it is the average of the points in a motif or unit cell. So this is already a very strong invariant, and you will see maps of crystallographic databases based on that invariant, but we can make it even stronger. So instead of averaging, we could keep distances per point. So for example, again, if you have the square lattice, then with pointwise distance distribution, so distances written down to neighbors per point, this distribution consists of a single row, because all points in a square lattice are equivalent to each other under translation. So 4 distances equal to 1. But under small perturbation, our unit cell can change. So this is a small perturbation chosen to make all numbers simple. We can easily get a 4 times larger unit cell. However, distances actually changed only a little bit. So I pushed up one point by 0.1 and this point down by 0.1, so that the distance now between them is 1.2. So this number appears here. And the smallest distance now becomes 0.8 for simplicity. So as you see, all distances, they changed only a little bit. So they depend on this small perturbation epsilon. And what we formally proved, that if we shift every point in a periodic set up to small epsilon, then the pointwise distance distribution that we compute here changes continuously in a suitable metric. It's called Earth-Miller's distance here, although many other metrics are also possible. So it changes continuously up to this upper bound 2 epsilon. And 2 epsilon can be easily explained for 2 points, for example. So forget about periodic crystals. If you have only 2 points and you shift every point up to epsilon, then the distance between these 2 points changes by at most 2 epsilon. And this theorem is simply a generalization, so a big generalization of this this result for two points. So next, well, we have already applied this PDD to predict new materials. So we can do it not only at the atomic level. In this particular work, we used centers of molecules. So yes, so these molecules look very different. Well, they're similar, but still rather different by size as well. But nonetheless, if we consider only molecular centers, then there is clear visual analogy between packings of these molecules, different molecules in real crystals. And this similarity can be captured by our PDD invariant as well. So that's how it's predicted the new material from a previously known one. Okay, so the main results, the strongest results about this pointwise distance distribution are the following. So first of all, we don't consider this k, the number of neighbors, even as a parameter. We consider it as a degree of approximation, because k simply measures how many distances to neighbors we put down into our distribution. If we increase k, all computed distances originally computed remain the same. We simply add more information, so more distances, so making our invariant stronger, but without changing all previous computations. So that's why this k is similar to the number of decimal places on a calculator. So if you'd like to have more exact number, you increase k. But usually we run our experiments up to, say, 100 atomic neighbors. So the strongest theorem here says that we can reconstruct almost any periodic set of points, so-called generic periodic set, from a lattice of this set and large enough pointwise distance distribution. And this result here says that it's fast to compute in near linear time in both parameters, k, the number of neighbors, and m, the number of points in a given unit cell. Of course, we applied it to the Cambridge Structural Database, the largest in the world. And to our surprise, it was already 4.5 years ago, we found several cases when the distance between our invariant was exactly 0. So we looked at the input files and understood why it was 0, because the input files had exactly the same geometric information, unit cell parameters identical, fractional coordinates identical, but one atom, so in this particular case, was replaced with a different one. So our colleagues at the CDC looked at the raw data, structure factors, and found then that they are also nearly identical, almost to the last digit. So that's why all these pairs that we found already several years ago were under investigation by several journals for data integrity. Okay, so more recent story. In November 2023, Nature published 2 papers. So some of you might know Google's GNOME dataset, this big claim, and Berkeley Lab that claimed to synthesize 43 predictions. So of course, chemists were skeptical from the very beginning, and this is the review concluding that none of these materials were new, but this review considered found duplicates or near duplicates of the reported crystals by unit cell search, essentially manually, and initially concluded that a small number of crystals were correctly identified. And we showed that, but were already known, although not in the training data for Google GNOME. And we have shown that actually this small number is exactly 0, so all crystals had duplicates in the CSD. And this is one missed example when you have here specific references. So on the left, the crystal structure claimed to be synthesized by A-Lab. The middle structure was found by manual unit cell search. so deposited after Google started training. But we have found even closer near duplicate, but with a different unit cell, so closer by our invariance. So now Google's GNOME itself, so it made public about 384,000 crystals. And yeah, the review of this work was also done initially by chemists manually. And then our reviews appeared in these papers. So let me show only the summary. So first example here. So 3 crystals from different databases and even with different compositions, but geometrically are nearly identical. So perturbation up to a very tiny fraction of 1 angstrom. So geometrically nearly identical and suspiciously different compositions. So when we change atoms in this way, we expect that geometry should be perturbed more than up to this small amount. Okay, now even without any perturbation, what we found in the GNOME, that there was a quadruple. So here group size 4 means that there was a quadruple of files, so different entries in the database where sieves were identical as texts. 1 quadruple, 43 triples, and more than 1,000 pairs. After that, we compared all sieves in the GNOME database by geometry only, so not including chemistry, only unit cell parameters and fractional covariance, and the number of duplicates have grown substantially. If you start rounding these numbers to 4 digits or 2 digits, then we have even more duplicates as a result. So this is probably the most striking example. So not only a pair of duplicates, not only duplicates, but also, as you might notice in the screenshot of the sieve file, they have even duplicate atoms inside the sieve. So 2 pairs at exactly the same position, identical. Right. So I should finish soon. So let me only highlight that this story appeared in Chemical and Engineering News in December about duplicate structures in many databases. And in January, Nature corrected the A-Lab paper by removing the word novel, not only the title, but in many other cases. So crossing out the word novel and discovery throughout this paper. Right. So to finish on a positive note, what we have done, we have mapped any periodic crystal to a set of atomic centers, so initially forgetting chemical elements. And what our comparison has shown that we can actually distinguish all chemically different crystals by using only pure geometry. So this map from crystals to sets of atomic centers loses no information. So it is injective different crystals mapped to different sets modular rigid motion. And here I include the photo of Richard Feynman because this picture and this table were redrawn from his first lecture on physics, atoms in motion, and with very simple examples. So 7 cubic crystals, but all different by comparing them purely geometrically. So this was an inspiration for us to state it as a crystal isometry principle. So different chemistry means different geometry. On the final slide, so the vision of the crystal universe, what we have known in the past, we had databases of experimental crystals, we had CSP landscapes of simulated crystals, but not even with a reliable distance between them. So we have seen essentially only approximations to stationary points, not necessarily even energy minimum. They could be stationary points, so similar to mountain passes in this photo, but everything else was covered in the fog, and our aim is to remove this fog and show the whole space for you. So Dan will do it in his presentation shortly. I finished. Thank you.